Well, hello everybody in Advanced Digital Logic. The video did not record from the classroom, or more correctly, I've got the video, but the sound is like really horrible, pretty much not understandable. So I'm going to attempt to kind of recover the stuff we did in class. I'm going to break it up into video chunks. This one I'm going to cover the material. There'll be a separate video for talking about the syllabus stuff, but this one I figured is probably the more important for most of you. All right. So, what we had talked about on Tuesday was dealing with, first off, semiconductors. And semiconductors, when we look at them, are partway between, say, or the boundary zone between the metals and the non-metals. So, if you think about the periodic table, our semiconductors are basically going to be in group 4 on the periodic table. Right, so there's carbon, silicon, germanium. Um, Obviously, these two for our computational area are the ones we're going to care about. Interestingly enough, carbon is right in that zone, and it is part of the reason why we are so successful as a life form and why we can do things is because carbon is in this same kind of area. The ability to switch between or have properties similar to metals and nonmetals, and that you can basically get them to perform in different ways is what makes it so flexible for life as well. Um, and then, in addition to the group 4s, we can also have something that's nearby. So, gallium and arsenide or arsenic, we can take gallium and arsenic and we can combine them to make gallium arsenide. And that, even though it's a 3 and a 5 in the table, uh, will kind of perform similar to the way that a group 4 would. So gallium arsenide also as a compound will behave like it. And you'll see other ones that are out there. Silicon, germanium, gallium arsenide are definitely the most common that are out there performance-wise. Okay, so that gives you kind of the first cut, right? This is which compounds and how can you understand how from the pure elements to the compounds, which ones are going to exhibit behavior that we want. And obviously there's other ones around there, but we're just going to, for our purposes, care about the big 3 right now. And I'm going to just kind of consider that I've got a group 4, and I'm just going to deal with silicon for our discussion, but you could obviously swap in other ones. Each ones are going to have a little electronegativity difference between them. There'll be a little bit of difference in their energy levels, which will make a difference in the voltage of a PN junction that's in there. So for instance, silicon, we get about a 0.7 volts to activate it. Germanium's usually right around 0.3, somewhere between 0.3 to 0.4. Gallium arsenide is usually a little bit higher than silicon. Somewhere around the 0.8, 0.9 zone would be reasonable. But anyway, they're all in this area. We want things that are kind of under a volt. And these are the ones that kind of meet our needs. Silicon is by far the most quintessential, so we're going to move ahead with that. So I'm going to erase these off here. Now, when you consider silicon, we're going to consider the outer shell. Remember the basic structure that you have of the periodic table, right? You've got the 2 outer element columns, and those ones are your S shell electrons. So for silicon, your S shell, right? So it's not just for silicon, for everything. S shell is the spherical. There'll be 2 electrons that are going to fit within that. And then the next level down, you'll see we add in a group of 6 more. Those are for the P shells, right? And the P shells kind of look like lobes sticking out. And you get 2 electrons for each one of those. Now, they don't add in 2 at a time. You'll get 1 at a time filling them, and then you'll start adding the other ones in, because there's actually a slight difference between the spin up and the spin down electron. But this kind of gives you an area. We've got 8 for the outer shell, and that's the structure of the periodic table you see. The next kind of level down is the D shell, but we're not going to need that at all for our discussion. So we've got these 8. Silicon has actually only 4 in its outer shell. So it either wants to gain 4 or lose 4. And it's that kind of in the middle zone that lets it behave like a semiconductor. Um, so when silicon comes near, so we'll often draw it kind of this way as put the electrons around silicon. If another silicon comes nearby, it will also bring 4, and they can kind of share a pair over here. And if you get another silicon, right, it'll bring it. And we get another kind of shared pair here between them. So as I start filling in silicon all around, each one bringing its 4 outer, they share those areas. And effectively, we see kind of like what looks like a completed shell, which is what all of these want to get to. Um, and it makes a very nice structure, which is why silicon makes these nice flat layers. You can imagine this pattern kind of goes throughout our whole system here. And you can imagine it continues on in all directions. Now, when we look at this, each one of these silicons, right, we have these electrons. So if we consider how much energy each electron has, and we'll think of this energy, like this is how much it has, that's the true thing, but you can kind of think of it colloquially, kind of like a distance. How far away is that electron? Now, I commented in class that this is not really true. It's not really a distance because this is a probability cloud that's in here. And it's not really even a sharp boundary, but that's basically, if you look at the density of the probability, they kind of have this general type of a shape to them, but it's fuzzy. It's, as you move away, there's no precise boundary to it. And in truth, the idea that electrons kind of swirl around it is not true either. An electron that follows a curved path in an electromagnetic field is going to, basically radiate energy, right? It'll emit photons and things, so it'll send off. So if you have an electron pass on a curved path through that field, energy comes off. That means the electron loses energy. And so if it was actually orbiting around here, since there's a field because the nucleus is charged, that electron would be constantly losing energy, which means it has to spiral in. This is not like a gravitational situation where you can just kind of hover out there in a rotation. No, right? As it circles, it would actually be radiating, which means it would collapse in, and we'd really have a lot of problems with matter if that was the case. So the electron itself is going to, if you observe it, it'll kind of collapse, however you want to think of it. I kind of like the Copenhagen description because I think it's easier to think about a collapsed particle and it's here at the moment than to think about many worlds, and it could be in all these different positions, but you still have the collapse. So in every one of those, it's in one spot. So we'll think about just one of those many worlds and the collapsed wave. But if you want to, I don't really care which interpretation, they're equivalent in some sense. I just think Copenhagen's a little bit easier. So if you think about for these probabilities and this electron traveling around, normally it's spread. The electron is not in one spot. It's kind of all over as a probability. It gets observed. There's some other interaction that causes it to become to a precise area, and it's going to travel basically in these straight lines. So it's not radiating energy, right? And then it'll fuzz as it's going through, and it'll go back to the probability, right? Observe, collapse, then start spreading back out again, and going to it. So that's really what's happening to it. Now, each of these electrons, as we mentioned, right? So that first one, the S shell, is fairly low. There's all the other ones in the earlier shells too. So you've got electrons at different levels, depending on what the particular, whether it's silicon or germanium, will depend how many different levels you have, right? So I've got all these different levels depending on on what the particular atom is. The highest filled shell is what we call the valence electron. Okay? And there's, for every particular nucleus we have, there's predefined levels, even ones that aren't filled. They can only take on this part of quantum. It's quantized. There's only certain energy levels that you can actually have electrons at. So the next one above valence we call conduction. So as you're looking at these, you end up with a pattern that looks here. Now, the Pauli exclusion principle tells us that no two particles, like electrons, for instance, can have the exact same quantum state basically in the universe. So when we've got another silicon atoms that's coming close, like we do in this matrix, each one of these have this same diagram, which means they're basically at the same energy levels. So what happens is it causes them to just kind of split just slightly, right? And there's tons of these. So there's lots of these little splits. And basically right around here, you'll get right a region basically for each one of these. And it'll look like not just one band, it'll look like a whole little region here. So we call those the valence band and the conduction band, because you've got a huge number of these, and Pauli causes the individual energies to split of each one, and so you get something that looks like a small region where they can lie within. Now, in truth, we can just consider kind of one of them, because we'll draw an upper and a lower. I'm going to zoom into this portion here so that we consider here's between, say this is the start of conduction up here. Conduction, and this is valence. And we have this region in between them. This is obviously energy going up in this direction. And I'm going to, in this direction, do the probability that the electron is there. Now, between the valence and the conduction band, there is this level which we're going to call the Fermi. Fermi energy, right? Which is at this level. That's kind of what the intrinsic amount of energy available is on here. So at, this right here is where pretty much the energy that's available to all of them. And this is where we're going to line up between any of these different graphs. It's going to line up on this Fermi energy. Now, if we considered at absolute zero, we would get a probability that kind of looks like this, right? You'd be right at this Fermi and below, right? So if this is probability of 0, probability of 1, right? No electron at absolute 0 would be able to go above the Fermi energy. It doesn't say the electron's not moving, right? It's just saying probabilistic, it's never bouncing out of that state. It's staying in the state that it's in. That's what you really get. As you raise the temperature, you start getting these kind of more rounded outs, right? So as you start raising, I think I drew that backwards. If you look at your probabilities that's on here, actually your highest probability is you're down here, but you do have a small probability that you can get higher. As temperature gets higher and higher, right, you'll start to get a chance that you're in the conduction band. So I did draw that. Sometimes I draw things backwards. So that's the thing for a second. Right. So I do have a small probability that I am up in the conduction band for this. And obviously the warmer I get, the higher that probability is. And it's basically from that curve, right? So the temperature is going to give an energy to them. That energy will connote to a probability. There's a chance, right? It could be staying down in its valence band, and that's going to be most of it. But there will be a small chance that it is actually here. There's a lot of chance it's over here, obviously. And as the energy goes up, right, you'll get a lower chance here and a bigger chance that it'll bounce out. Um, but that's in essence what temperature means, right? The available energy for it to move about. Um, if the electron makes it up to the conduction band, it can kind of move about our material, right? So this is when you're free to move about the country up here. Right? All right, that's for our semiconductor to be able to conduct, we need electrons up here. That's the basic idea. Okay, now we look at this and we go, it'd be really nice if I could make this a little bit easier. And for some things like silicon, right, this energy gap from where the Fermi is to the conduction band, can be fairly high, right? We rate these in electron volts, and it's like 1.1 electron volts. So, you don't get a huge number. You definitely get some, but it's a little bit of work. So what we'd like to be able to do is to say, hey, how could I get more electrons up there? Well, what I can do, right, this is an intrinsic semiconductor. Intrinsic means it's a pure material, and this is intrinsically, just on its own, what does it do, right? And there's a chance, based on these energy levels, where your Fermi energy is, what your temperature is, that you get electrons up in the conduction band. Now, let's say we were to come in here and we were to make an extrinsic semiconductor. Now, an extrinsic semiconductor, we dope in a material. And doping means I'm going to replace it. So let's say, for instance, that we pick one that's in column 5. So, whatever, we put in, right, the arsenic, right? It has 5, so we've got the 4 it was sharing, and it's got 1 extra. What's going to happen? I do this throughout the material, right? So not just one, but I've got a decent fraction of them. So there's a bunch of those little free electrons, right? So that means overall there's kind of more electrons here. So we call this an N-type material, right? N-type mean there's more negative charge carriers. Now, an N-type charge carriers like this that we dope in is going to actually move up. This is for the N types. Based on how much you dope and what the material is, it will boost this level up, right? Moving up where that Fermi energy level lies. The N-type materials, it's closer to the conduction band. So now, when you get these kind of low-level areas, like this same one, right, is effectively going to look like it was here, right? So for that thick band, it's going to look like that. So I've got, at a lower temperature where I was here before, now I go up to here. As the temperature goes up to each of these successive ones, right, the next layer out, you can see I get even more than it was before. So I get more and more likely that I'm going to be able to have electrons in my conduction band. So it makes it a little bit easier for charge to flow. That's the whole idea with your N types. P types is I replace from the other side. So instead of arsenide, what if I used gallium that was on? Gallium would only have 3, so I would replace this one, say for instance with gallium, and it is missing an electron. So we draw that little blank hole there. That is going to the P types for positive charge carrier. We'll talk about that in a sec. Are going to move your Fermi energy levels down towards the valence band. So when you draw those same probability temperature curves, it gets less likely that you're going to have material. Not 0, but smaller. Definitely smaller. So it kind of bumps down where your Fermi energies are towards the valence band. Now, it's obvious why electron is negative. A hole, imagine, on any one of our things, one of these silicons, the electron popped out and it started moving around through the system. So I got my electron kind of floating around. In essence, there's more positive charge carriers in the nucleus than can be blocked by all these electrons around it. So you're going to see a net positive charge. So it looks like that empty space has a charge. It's really actually the nucleus that you're seeing because there's no longer an electron to balance it. But um, essentially, we call those holes positive charge, um, even though it's not actually, nothing does not have a charge. But it's simple enough to kind of work that way. So that's why we say holes have positive charge and they move about. But what you'll notice is it's able to get things by an electron from somewhere, kind of pops up, travels around, and falls in the hole. So maybe I have an electron from over here, pops out, and it travels along, and it falls into here, and it fills this one. Right? When it does that, that's going to look like positive charge going this way will look like a negative charge going that way. That's why they're equivalent. It's a little more work, though, because somebody, probably from the surrounding silicon, pops up, travels over, and then falls down into these holes. And it kind of moves. Then some other electron someplace can move here. P-types tend to have a lower current to it because it has to pop up, move, fall in, whereas the electrons just have to pop up. It's a little bit less work, so it's a little bit faster on the N-types. But that's basically how the P and N's work and why it's holes in charge carriers. And what looks like a positive charge, right? So this one getting filled looks like you have negative stuff or positive stuff going away. It looks like this became positive over here. So it looked like a positive charge traveled, even though it was an electron traveling that way. Okay. Hopefully that makes sense as you're going in. I'm not going to have you calculate the probabilities here. This is a subject for electronics. What I need is for you to have the intuition of how this works and why it works. And I want you to have a correct intuition, which is why I'm explaining to you the Fermi stuff, at least at a high level. Then when you go into electronics and they have you calculate the equations, it'll make a lot more sense why the equations and everything else you get and why it works the way it does, because you've kind of got a picture in your head that correctly functions. All right, let me erase this. Imagine I've got, right, so that was a P-type with a gallium. Imagine I take a block of N-type material and I stick it next to a block of P-type material. Now, our P-type material has a whole bunch of holes all throughout it, which creates that kind of net positive charge. And the N-type has a whole bunch of electrons sitting around. And what will happen is you'll find these electrons will kind of drift around and they'll hit these holes. And then that electron gets locked up. So this is no longer here and this one's filled, right? And this one travels along and fills here. So these kind of get locked up, right? So you'll see these go around and fill in things. And you'll get a region right around here where everybody's kind of cancel each other out. And, you know, the electrons here are kind of stuck in the holes and the holes are gone. So there's no charge carriers. So this is what we call a depletion zone. Now, there will be an intrinsic charge because now, remember, we dope these holes in. So we actually have a slight negative charge over here and a slight positive charge here. So that looks like a battery, but it's kind of in backwards. So that's, in essence, going to create a barrier for us that is going to prevent, right? I can't get any conduction through here. This battery that's kind of induced by these electrons falling in the holes is going to basically preserve this. So you're going to get this little region where things won't work. Now, if I were to hook this kind of in backwards, well, I put a positive side over here and a negative over here, I reinforce this, and this depletion zone will grow. All right. So this is what's called reverse biasing. So if I reverse bias my circuit, the depletion region grows, things cancel each other more, and it's even less likely that you're going to get any charges that are going to flow here. But if I forward bias it, I put the positive on here, the minus on here, what will happen, right? So this didn't happen because I didn't hook it backwards and reverse bias it. If I put the battery forward bias way, positive for the P, the minus on the N, it's going to start opposing this one, and this depletion region will now shrink. And if I make the voltage big enough here, which for silicon is 0.7 volts, it'll actually cause this depletion zone to completely go away. At which point I will have charge carriers on both sides ready to take care of things, and now it flows like a nice wire should. So if I put the battery backwards, it doesn't flow. Well, if I put it this way, it does. So you can kind of see this area, your P to your N, right? If you were to hook the plus on this side, the minus on this side, it sees a wall. If you put the plus on this side and the minus on this side, it's got this nice little arrow going through. So plus the minus. Now, in truth, if that feels backwards to you, because it always bugs the heck out of me, plus to minus, we're always saying the conventional current flow is flow of positive charges. This is actually a mistake made early on, because when people were first looking at it, in particular Ben Franklin, when he was first looking at this, was it the negative moving or the positive moving? Mathematically, it doesn't make any difference. Physically, it does. But mathematically, it didn't. There was no way he could tell which one it was. He took a guess. He said positive moves. Turns out positive's in the nucleus. It doesn't move. So now we've got this kind of backwards thing. So if you ever do get a time machine, you are sworn now, your first action will be to go back to Ben Franklin and tell him the minus charges move. And nobody will have to deal with this kind of backwardsy portion. But we're going to say things are flowing from plus to minus, conventional charge carrier. And that's why I say if you put the plus here, it'll flow this way. Technically speaking, if you put the plus and minus here, the electrons flow that way. But if you do that, it'll look backwards with the picture. So the pictures are all based off Franklin's conventional charge carrier flow. We're probably too far in this to ever reverse it now. So here we are. But anyway, that's the basic thing, right? The plus to the minus, it flows. If we were to look at this and plot our current, so if we had our current I versus our voltage V, right? Once we get to that kind of 0.7 zone, we get a very rapid uptick, assuming this is against silicon. Right? We had a lot of current for almost no voltage because it's like a wire. But I'm exaggerating this down here. There's a tiny backwards one if your voltage is flipped, so it's a negative voltage, right? Reverse direction. You will actually get a tiny current flowing. It's really, really small, but it does happen. Some of that's going to happen. You'll get electrons that will just tunnel from one side to the other because that whole probability thing. If you do it too far negative, it'll actually basically kind of break, so to speak. And then you can run into problems. You'll get this avalanche region. We're not going to worry about it. We're going to stay nice and safe within a zone here. And in particular, we're not even going to want you to go too much past the 0.7 because if you get too much current flowing, your heat is going to be basically proportional to I squared. And that's going to go towards infinity really fast. So you will burn out your chip and destroy it if you apply too much beyond that. So we're going to assume you're going to stay really close to that 0.7. We'll put resistors in to protect it. So if your current starts flowing, that resistor will take it and basically what's called a current limiting resistor. It will limit the current flow because the resistor will actually take it off in a linear line. Then it'll take over from the diode. Limiting what the current is because the diode will not limit it. We don't want to go this way because we don't want to get into that kind of avalanche region, which could also damage things. So we'll stick in kind of this nice little operating zone. And usually, actually, most of the time, like right here, right, where we'll be from like 0 and up to 5 volts. But like I said, that 5 volts we'll have resistors to protect us. So how does all this fit in with here? Right, we've got a little bit of hand wavy. I want to give you a tiny bit of connection here to what we talked about on this side. So imagine we take these, and we're going to take the N and the P material, and maybe I'll try to match the colors too. So imagine I've got this and my P material. My N material I did in purple. That's probably bad. I probably should have done P in purple, but oh well. They're going to match, like I said, on the Fermis. So the N type, remember, it's up here. That's my Fermi level. My conduction is really close to it. And my valence is way down here. Okay? And this, from kind of that middle zone, was that difference for the N type. Now the P type had gone the other way, but it's got to match where the Fermi energy is. Its conduction is down here. And it'll just kind of curve up, and its valence is up here, because from the old one, this difference here is your P doping. And this is then the energy difference that's going in. This differential here, it'll kind of spread out a little bit, and that energy differential is what's creating that depletion zone, causing the electrons to move from this side to this side, and the holes to move from here to here. Because holes want to fall down, and electrons want to go that way to rise up. So you can think of the electrons kind of going up, gaining. Right, that's what they want. Right, so that's going to shift in, but always the Fermi has to be kind of constant as it flows. So if you reverse bias it, you make this even worse, right? Because you got these things to scale basically once they've equalized out here, and when you're reverse biasing it, you're kind of matching them, right? So you're pumping the energy so they're equal. The conduction. I did that backwards. Valence. So I told you I do this sometimes backwards. Conduction band's always on top. In order for them to flow this way, right, the electrons flow this way, the positives to go that way, it's got to make it up that wall, right? Versus the positives, it's got to go that way. So that's why it doesn't flow easy. And, you'll get that initial spread, and then it's just no more. Reverse bias, you make it worse. Forward bias, you're going to pull these together, and you're basically canceling off that amount, because this plus that is going to give you what that differential is. And that's basically from this point of view, right? So you can see here on the energy charts, if you have the same exact material and you're doping the same and everything, these will be nice and symmetric. In reality, you don't always do that, so they're not necessarily symmetric. But simple case here. All right. So anyway, you can see on the energy levels, you can see it as kind of an example on the flows. Either way you like to think of it, you can get the idea of how they're going to be able to cancel and work out. So that's what basic things for how the materials will work for us. And that's what I wanted you to walk away from first class. You hopefully remember how all these function. You got an idea about basically energy levels and everything else. Just as a note, if you consider this pictures that we've drawn here, there are other ways to get the energy to make it up that kind of cliff, right? So you can think of an electron here, right? It needs more energy to get up here, right? In order for it to flow, it wants to get up there, but it doesn't have the energy to get up there. So how can it do it? Well, you either create an electromotive force and lower it, or what if it got more energy? Now, it can get more energy just from temperature, but it can also get more energy by light striking it. Right? So if light comes in and hits that electron, it can take the energy from the photon, which can give it enough energy to to pop up here. This is actually what photodetectors do. It's basically just p-n junctions, and the electrons on one side will get hit and they will bounce up and then they can flow. And the more light that strikes them, particularly the more light that gives them the right amount of energy to make that jump. So that's how you can adjust the frequency of light. You do it by how much energy is carried by it. You'll be able to jump up and you can detect them. Obviously, a little bit more energy will still help it to go. Right? If it's too much energy, it probably won't get absorbed. So you have to have the right band gap. So you can adjust them so they're sensitive. Similarly, right? So that's how a photodetector works. What if they go kind of the other way, right? You put the plus and the minus, so things are kind of going that way. What happens here when things are moving and they're dropping in their energy levels? When they drop in their energy levels, they've got to give off, right? So when they give off energy, they emit light, a light emitting diode. So you can actually get the ideas or understand that every p-n junction actually emits photons. They may or may not be visible. Based on how that energy gap is, will tell you basically what frequency of light you're going to get, i.e. what color is the light. It'll also tell you what quote unquote color it's going to absorb, right? It might not be in the visible spectrum, but we'll consider ultraviolet and infrared and everything else as colors too, in this sense. So we can say colors emitted and colors absorbed. But it all comes from this basic idea here. And it will allow you to scale it even without a voltage applied for the detector side, thereby giving you your detectors. So anyway, a proper understanding of this will help you understand a lot of different devices, I guess is the long and the short of it, which we'll be using in a bunch of different areas. So hopefully this makes sense, and we'll move into next class how we can use these to build some helpful gates for us, and that should be good. Hope you're having a great day. Bye.